All right, so this video is going to help you answer the questions about looking at graphs and determining the rate law from the graph. So in this method, you can use one experiment to determine the rate order rather than trying to use multiple experiments to determine the rate order. Now, this works best if you really only have one reactant that is changing over time. So in lab, you're going to be looking at an example where you have an abundance of extra reactants and it's only the limiting reactant, the crystal violet, that is changing concentration. This also works best when that concentration can be easily and quickly determined. So because crystal violet has a very distinctive color and the product that is being formed is colorless, it is easy to determine how the color changes and use that as a proxy or a substitute for what the concentration is doing. So let's see how this works. When we have a graph of the concentration versus time, everything that we have looked at so far has looked like this. It's been kind of a curve where it sort of bows in towards the origin, and it looks like the rate is slowing down over time. And most reactions are going to do this because they're going to depend on the concentration of the chemicals. If there is no dependence, though, say you have 3 or 4 reactants and one of them really isn't part of the rate limiting step, then this would be a straight line. So just by making that graph to begin with, you can identify whether or not it is a zero order reaction. If you have a straight line looking at the concentration versus time, it's a zero order reaction. Or if you have a proxy, a substitute for that concentration, like the pH or like the color, something else that changes proportionally to the concentration, then you can also do that kind of visualization there. Okay, so as the reaction progresses, the concentrations of the reactants and the products are changing. Here we're just looking at the reactant N2O5 or dinitrogen pentoxide. Now you'll notice at the bottom here, in addition to having a column with the concentrations, we also have 2 more columns. And they have the natural log and they have 1 over the concentration. And so we're going to look at in the next few slides why that is important. But let's just remind ourselves that the slope of the line here, the rise over run, is the rate. So the change in the concentration, that's your rise, over the change in time, that's the run. That tells you the rate. And so when we take any 2 points, what we're looking at is the average rate over that period of time. And we also know that for a first order reaction, the rate law is rate equals K times A, raised to the first power, which we don't typically write. So what I'm going to show you on the next page is the calculus that gets us there. If you haven't had calculus or if you're not really interested in it, you can fast forward and get to the highlighted equation at the end of the video. But basically, we're going to use calculus to tell us how we can find that slope at any given point without having to go and know multiple points along the way. So here we have the average rate over the whole time, a smaller time, and an even smaller time. Calculus just makes that teeny, teeny, tiny interval so small that it is essentially 1 point. Okay, so for first order reactions, we say that the rate is equal to the change in concentration over the change in time, but we also know the rate law says that rate is equal to Ka. So we have 2 things that are equal to one another. This is where the calculus comes in. We're going to use D instead of the triangle to represent that change. And we're going to move the dt over to the right side. And then we're going to move the A, the concentration of A, over to the left-hand side. So get the like terms together. So we've gathered all of the concentrations on one side, and we put dt out of the way so it's not with it. So when you take your second semester of calculus, you will probably learn to do integrations. And with the integrations, it looks like this. And so we are going to integrate this. And the result of that integration on the left-hand side over a given period of time is going to be a natural log. Okay. And on the right-hand side, because t didn't exist in the equation, it just has the change in t, we just end up with a constant. And so we have the constant times t, and we have the natural log of a. But we have these symbols over to the side, a line with a 0 and a t. So basically, this is telling us how much that has changed from 0, time equals 0, to time equals t. So that first little interval that we have. And calculus also tells us how to spread that out. So when we do, we get this equation. And notice that we have in here the concentration of A at time t. This is what we're interested in, any given point. And then over here is that time. Here we have k times 0. Now k times 0 is the same as anything times 0. It's just going to be 0. So that term's going to disappear. We also need to remember that when we subtract logarithms, and ln is a natural log, that's the same thing as taking the log of the fraction of those terms, or the quotient of those terms. So we can also write this equation like this: natural log of the concentration of A at whatever time t, divided by the initial concentration, the concentration at time 0. Okay, so that's the left-hand side of the equation. Right-hand side of the equation is just, we got rid of the 0 times k. So one way to write it as like this, the other way is to spread everything out. And the reason we like this last equation is that that sets us in that form of y equals mx plus b, which is what we looked at on Friday for determining how the graph is going to show us what's going on. So y equals mx plus b is the equation of a straight line. In this case, y is the natural log of the concentration at any given time. So here's our concentration, and here's the natural log. This whole thing is y, not just the concentration, the whole thing, the natural log. And then on this side, we've swapped these two terms. So x is the same thing as time, right? So whatever is next to x is going to be our slope. And that means negative k, or the opposite sign of k. Remember, k is our rate constant, so we might be interested in that. B is the intercept, and so this is going to intercept the y-axis at the natural log of the concentration we started with, A equals 0. Okay, so y was natural log of AT, x was t, B is natural log of A0. A0, concentration of A0, is the initial concentration. So that means if we have any two of those things, we can find the last thing. And this is what our graph might look like. Now, often our concentrations are less than 1, and so these numbers over here, because logs of numbers less than 1 are negative, like log of 0.5 is a negative number, these will end up being negative. Don't worry about that. What we are concerned with initially is just, is this a straight line? If this is a straight line, that tells us we have a first order reaction. If it's not a straight line, we don't really care about this graph at all. Okay, so when you're in lab, if you make this graph and it turns out to be a straight line, great, you have some other steps that you can do. You can look at the slope and determine what the value of k is. You can figure out what your initial concentration was, or in this case, the proxy, the initial color. And you can also figure out half-life, which we will get to later. Okay, for a 0 order reaction, we said the rate doesn't depend on A. So when we do all of this, we just end up with what we would expect. The concentration at any given time is just going to be equal to the initial concentration minus the constant times the time. So it's going to go down because we're using it up a little bit, but the rate that it goes down stays the same. And so our intercept is going to be our initial concentration. So this would be our initial graph of the concentration versus time. This one's not very interesting, also not very common, so we don't worry about it too much. All right, second order. Here we have a faster change and more of a change dependent upon the concentrations change. So if we go through the calculus, set it up the same way we did before, putting all the concentrations on one side, putting time on the other side, then taking the integral of both sides, then we end up with this integrated rate law here. Okay, this is in the form of y equals mx plus b. So y is 1 over the concentration at any given time. Mx is the rate constant times time, and b, our intercept, is 1 over the initial concentration. So that looks like this. Notice this is an uphill graph, and there's no negative sign in front of our k. So whatever the slope is, that is k. These can be a little bit tricky because if our concentration is something very, very small, like 0.001, that's 1/1000th. Well, 1 over 1/1000th is 1,000. So we would be starting with 1,000 and getting larger and larger. So these graphs, the numbers can kind of look odd, but just trust your math and go with it. Okay, so for your assignment, you're basically looking at your graphs and saying, which one of these is a straight line? Then you check out the y-axis and say, which y-axis corresponds to this? So am I looking at 1 over the concentration? Am I looking at the concentration by itself? Or am I looking at natural log? All right, so here are the 3 different kinds. Now, these would not be the same chemical reaction because this first one is showing you a first order reaction, and that is always going to be first order. So the second one, which is showing a second order reaction, can't be the same thing as the first one. So it's different reactions going on here. But this is what they look like. Notice that on the bottom, we have time in every case. Notice that our slope is either k or negative k. So the number is always equal to k, right? And the big thing that changes is what is on the y-axis. So if I see a natural log, it's first order. If I see 1 over a, it's the second order. And if I see a, it is 0 order. So if I look at this data, and this is similar to what you're going to be doing in your homework assignment, you're going to look at each of these and you're going to say, which one's the straight line? Well, this is the curve that we saw when we initially introduced this. So it's not a 0 order, but this one looks like that's a straight line. So then I look at the y-axis and I see its natural log of a concentration, and natural log tells me that this is a first order reaction. Now, if I had the equation for the line, I would also be able to determine the rate constant. And notice with our numbers here, I told you natural log, sometimes we have negative numbers. That's what we see here. And with 1 over, we sometimes have very large numbers. So we see that here. Okay. These kinds of problems where we're trying to calculate this, we will be looking at later on. So I'm not going to go through this right now, but this should be enough to get you through the problems that were in your packet and to prepare you for lab. Good luck.